Good evening, everyone. Welcome to the NAST 2024 webinar series brought to you by National Anveshika Network of India, NANI, a proud initiative of the Indian Association of Physics Teachers, IAPT, and Shiksha Sopan. My name is Vimal Kumar, and I am thrilled to introduce our special guest for today's session on know-how of graphs, Ms. Sarmistha Sahu. As we gathered here on this fine Saturday evening, May 25th, 2024 at 6 p.m. IST. We are embarking on a journey of exploration and discovery. Today, we are privileged to delve into the intriguing world of graphs and fundamental concepts in mathematics and science that underpins much of our understanding of the universe around us. Ms. Sarmistha Sahu, a retired associate professor of physics with an MSc from Utkal University, has significantly contributed to the physics education through her extensive teaching career at Maharani Lakshmi Ammani College in Bangalore. And as a founder of Ammani IAPT Anveshika, renowned for her innovative approach, she is a six-time winner of the national competition and three times winners of international innovative experiments and three-time winner of the national competition of innovative computational physics. Ms. Sahu has authored the comprehensive series Understanding Physics and Concise Physics, each spanning 8 volumes, and has published numerous research papers in both international and national journals. Actively involved with the Indian Association of Physics Teachers, Indian Science Academies, and Agastya International Foundation. She has conducted countless workshops and science demonstrations inspiring many students. Her dedication extends to women's development, having been involved with the Women Development Center for 5 years. Proficient in multiple languages and skilled in various computer applications, Ms. Sahu is committed to making science accessible and engaging while also enjoying personal hobbies like embroidery. Graph the future, mapping pathways to knowledge and discoveries. This will be the last webinar of the NAST 2024 series, and we have allocated 1 hour and 15 minutes for Ms. Sahu's enlightening presentation, followed by dynamic 15 minutes Q&A session. So grab your pen and paper for note-taking and get ready to engage actively. Your participation and insightful questions are highly encouraged as they will enrich the discussion and contribute to the unparalleled learning experiences. Let's seize the extraordinary opportunity to learn from one of the greatest minds in physics education. Thank you for joining us, and let the adventures begin. Welcome.
A very good evening to all of you. I hope I am audible. Can I get a feedback saying that you can hear me? Okay. So I'm extremely happy, and a special thanks to Shiksha Sopan and Mr. Bimalji for inviting me for this particular event. And I'm absolutely grateful to Professor H.C. Verma, who has inspired me to be a part of NAEST. And I feel absolutely proud to be amongst students, young minds, who are all ready for adapting to different skills in experiments. So welcome all of you. We will go through this session of know-how of graphs. As the topic suggests, I'm sure I'm going to talk only about graphs at the present. I'm taking a little longer than allotted, especially because I want all of you to go through all the different aspects of graphs that will be needed for our experimental skills that we are embarking on. Okay, so give me a little time to go through each one of them so that you understand. And unfortunately, this Zoom meetings are a little barrier in the sense I'm not able to see any of you, though you can hear me and probably see my picture, but I really cannot interact the way I would love to interact in a classroom. So all that I expect you is, I will like to put questions, but since there is not much time, maybe I will not stop to get an answer, but I would love to have all your answers in the chat so that we can go through them one after another to see how much of it you have understood. And in any case, whatever questions you have and you would like to ask there and then, since we are not able to see each other, I may not be able to stop immediately. So please put your questions also in the chat so that I will spend some time going through the questions and we will see how best we can satisfy each other. Okay, so now I will start by presenting my PPT so that we can see and listen to whatever is meant to be heard about that. So first I will share my screen. Is the graph PPT visible?
Yes, ma'am.
Yeah, okay. I'll set it up so that I don't have any problem. Send request, ask admin to enable AI companion. Shall I cancel it?
Yes,
I think
ma'am.
I've cancelled. Okay, so this is what I would like to talk about. Mr. Vimalji has already told the topic. I again belong to Amani IIPT Anveshika, one of the Anveshikas that has been allotted in the country in Bangalore. Okay. So since we are going to talk about graphs, most of us know what exactly graphs are. In fact, we have already started from, yeah. Can you hear me?
The full screen, yes, ma'am. The full screen is not visible.
You want, okay.
Yes,
Is it okay?
now it is visible. Yes, ma'am.
I will do this. All right. Is that okay now? Is it clear?
Yes, ma'am. Yes, ma'am.
Okay.
Yes.
So now all of us know about graphs. So I'm not going to spend much time talking about the basics of graph, but probably a little more than that. So when we do an experiment, what do we get? We collect a lot of data. Now, if I want to tell anybody what my experiment was all about, I'm sure if I show them the data, it will not be very meaningful. Basically, because it will not really vividly clear when I tell what exactly I want to show them. So how do I go about? I think the graphical interface between people and data is necessary. To be able to visualize whatever experiments we have done, we require graphical visualization or interface. And what do we need for that? The two main things that we need are the data itself and the plan for representation. The plan for representation, of course, is the graph that we are going to draw in order to show what exactly we are talking about in the experiment and infer from that. This involves being able to represent the story from the data accurately. So how will we do it? Let's go through it. I will give basically a set of rules, some basic rules, and tell what exactly or how exactly we can improve our figure design. And of course, explain some common pitfalls that we do in our graph process. Okay, so that is how I will go about. Now, the first thing that we have to make a good graph is we must know our audience. What do I mean by knowing our audience? Let us take an example. Suppose the medical fraternity wants to make all the people around aware of all the different cancers that they are seeing in their creation. They should be able to show that what are the different types of cancers that are existing at that time. And of course, also tell us how many of them have been afflicted at that time and how many of them have died because of that particular cancer. So if they show a graph of this type that I'm showing over here, where they just simply list out the different types of cancer, and of course tell us how many are men and how many women have been afflicted by this, that should be enough, or maybe a little more. I'm not able to remove this from here. Okay, never mind. Okay, so what does the graph show? The darker bar graphs is telling us how many people have died of lung cancer, for example. and how many of them were men on the right-hand side and how many of them were women. And it also gives us a bar graph just behind it, telling us how many new cases are there. They don't give us in detail or in minute detail what exactly is the number. If they tell us that this many thousand people have been afflicted and of which this many have died, that should be enough. So for awareness purpose, this sort of graph is good enough. We don't have to go into the minute details. But what if it is a different type of graph? So based upon the audience, we should draw the corresponding graph. Does that make sense?
Yes.
Now I'm also pointing out that we have to adapt the figure to the support medium. I'm just giving you an example. Suppose I have done an experiment where I have 250 trajectories of a dual particle system. That means two particles have interacted with each other, and I want to show what their trajectories were all like. So I do them all one by one, and the left graph over here shows me how they all look. But if I am giving this as part of my publications, it is fine because the audience who will be reading this will look into my graph in minutely and find out what has happened in each case. But imagine, suppose I had to give this in case of a poster presentation. Now, in a poster presentation, people simply come, see your poster for a few minutes, try to grasp what it is all about in a short time, and then go ahead. For them, a detailed graph like the one that is drawn on the left-hand side may not be meaningful because there's definitely not going to read it minutely. So what can we do? We can just give the outline of the graph so that it is clear how the interactions were taking place, and that should be enough. So this is what I have been trying to show on the right-hand side, that the entire graph that I'm going to send for the presentation is not really necessary for a poster presentation. So depending upon the media, your graph should be aligned. Now, do we have to draw captions? Definitely, captions are not optional. If you until and unless you mention what the graph is all about, it doesn't make sense. So a person will not be able to tell what you are referring to in your graph. Therefore, captions should always be mentioned. Okay. The next thing that we need to do is do not trust the default. Many of us are using applications like Excel or other online applications for drawing graph. All of them have some default settings. So if I want to use the default setting, I can draw a graph quickly, but definitely it will not be as meaningful as I would have made it if I had labeled it properly. So I've given you a diagram on the left-hand side, which is a default diagram drawn by, let us say, a Python program. Here, the x-axis is simply a number line. It tells us that at different points on the y-axis ranges from -1 to +1. I'm sorry you're not able to see it. I think I don't have to have it over here. So the y-axis is ranging from -1 to +1. This is a graph. If you put a axis, maybe the y-axis, then you can immediately say that, okay, the blue line is a cosine curve and the green curve is a sine curve. But that is all about it. You really cannot tell anything more in detail. But suppose the same graph you had created and then labeled it properly. For example, give the phase of that waves that you were talking of on the x-axis, and then the y-axis always is marked. So you can now highlight them and probably talk about a particular particle, how it has been displayed. So I've shown it to you over here. Now immediately, and of course, you must have the legends to tell the person, whoever is reading, what sort of graph you are talking about. So it becomes very clear from the legend that the blue curve is a cosine curve and the red curve is a sine curve. Probably if you knew about it from the previous graph, you said that yes, blue curve is cosine. But here it is absolutely clear about it that this is a cosine curve and this is a sine curve. In addition to that, the x-axis is also telling us the phase of different points. So suppose I'm talking about a particular particle which has been displaced, and I've shown it as a dot over here. Now this point is almost at 2/3 of this distance. So therefore I know that the phase of this particle is equivalent to 2/3 of pi. And since it is a sine curve, the wave function must be equivalent to sine 2 pi, the particle displacement must be equivalent to sine 2 pi by 3, which of course we know is equivalent to 3/2. And that if you look on the y-axis, you clearly see that yes, the displacement is equivalent to √3/2. Okay, so you don't have to actually hunt for this. These are all shown over here on your graph, clearly labeled. Similarly, if the particle was displaced downwards at the same position, the same phase, then it would be equivalent to cos 2 pi by 3, which is again equivalent to -half. So if you look at the displacement over here, you say that yes, it is -half. So this is how it will make a graph clear if you label it clearly, so that anybody who sees at it immediately gets the gist of what you are trying to show. The next important thing that you should be doing is, most of us do use colors. So we must use colors effectively. Here again, I have given a sample to tell you what exactly I mean by color effectively. Now, most of these applications do have different sorts of colors. So I've shown you two such things. Suppose you had chosen a seismic color map where you are using the diverging curve with two colors, blue and red. It looks very beautiful. The blue and the red are alternating. It looks beautiful, and therefore you like the curve. But if you look at it intently, this is showing us some fringe patterns, bright and dark fringes. If you look at those fringe patterns, you realize they are not uniformly colored. The one at the bottom, if I'm taking only a small slice of that entire graph, let us say my y over here is equivalent to 0.2, then I realize that this fringe is darker at the bottom and lighter at the top. In fact, it is not uniformly colored, and therefore it doesn't give me the meaning of this bright fringe as I would have liked to show my students. And in addition to that, if you look at it as you go across, you know that the intensity is gradually decreasing. And of course, you also know that the width of the fringes are decreasing. But when you go towards the right further end, you look, or the color combination is such that it looks as if it is going to merge. But in reality, it is not merging. The intensities are gradually decreasing, but it is becoming narrower, but definitely they are not merging with each other. There are definite bright and dark fringes. But suppose I had chosen another graph, which is purple's color map from the same application, and probably even if I take a very narrow slit slice of it, let us say 0.1, and look at the pattern now, the same pattern is visualized over here. If you look at this, the intensities are gradually, contrast is perfectly fine. The bright and the dark are absolutely different from each other. And you are able to see the intensity difference definitely much better than the previous one. If you glance your eyes towards the right, you find that all the fringes are existing. They are not looking as if they are merging with each other. So the intensity pattern is much, much better over here as compared to the previous one. If you look at the curve that I have plotted over here at the bottom, you will see that the intensity on the right curve is much, much higher than the intensity curve on the left-hand side. So the same intensity pattern can look different depending upon the corresponding background or the color that you are choosing. Hope it is clear. Okay. And the most important thing of all is do not mislead your reader. I'm giving an example over here to tell what it is all about. Suppose you say you want to represent graphically the numbers 30, 20, 15, and 10. Immediately we know what is the difference between them, what is the gap between them. Suppose I want to show it to my readers what it is in terms of a graph. I can draw the graph in two ways. I will take these numbers and represent it in terms of the disk area. Okay, the black dots over here are represented in terms of their disk area. On the other hand, I can also do it by taking the disk radius. So if I look at the bottom one, the red graphs, as well as the black one, which do you think is representing the numbers 30, 20, 15, and 10 clearly? I wish you could answer, but definitely you can make out that the difference between 20 and 15, 15 and 10, and 30 and 20 are very well represented in the black dots as compared to the red dots. So it would be preferable to show it as the black dot shows rather than the bottom one. Another example, suppose in my class I have 10 students and all of them have gone through a physics exam and they have done well, according to me, and they have got some numbers which I want to plot them on a graph. Okay, so I take the ranges, let us say 80 to 82, 82 to 84, like that up to 100, and I want to plot how many of them have got in this range or that range. When I put all the numbers and make a graph, this is how it is. All these students have got marks ranging from 80 to 100. If I look at the tip over here, you will realize that it is they have got points from 80 to 100. But if I take only a slice of it, that means only this part of the graph I want to highlight, so which I have done over here in the red. If I do that, then the graph looks like this, where it shows that there is a difference between each of these bar graphs. But in reality, I realized that all of them were having numbers from 80 to 100. When I look at the red graph, does it give you the same impression? Definitely not. It shows that there was a lot of parity between the students when I compared their marks. So definitely it would be much better if the black graphs are shown rather than the red one. Perhaps it is clear now what I mean by saying that we need not mislead the reader. Another very important thing is, let's not give or plot junk on the graph. That means you give the your readers some junk which you would think will be clear enough for them, but it is really not. What do I mean by that? Again, I have shown two graphs over here. On the left-hand side, let us say I've done experiments on 7 series of samples, and I want to show the readers what is the difference between each of these samples, what are the similarities between them, etc. So what I do, I plot all of them on the same graph, one over the other. But to make it different, saying that this is series 1 and this is series 2, probably I give the legends of the different colors, saying that this is series 1 was blue, etc., etc., but plot all the graphs. And of course, give all the x-axis readings and the y-axis readings. Do you think anybody will be able to identify what is happening to the blue curve, where it is peaking, when the orange curve was not peaking, etc.? Will it be clear if you look at the graph, even though the legend has been clearly mentioned? Not really. In fact, even the x-axis, because there are so much of data, you are trying to write the x-axis up to 3 decimal places. There is not much space between the grid lines, and therefore they are overlapping. So though you are trying to put everything on your graph sheet, everything becomes muddled up. It's not very clear for a person to read it and tell that this is what is happening to series 3 or this is what is happening to series 4 at this particular point. But the same graph could have been done the way it has been done on the right-hand side. Suppose you put series 1, 2, 3, 4 all separately, but since you want them to realize what is happening to series 1 with respect to the others, all the other graphs can be sort of a little lighter or off shade so that you can see what is happening with respect to series 1. At the same time, it is not disturbing the look of the graph that you want them to see, or it is highlighted. So in this case, everything becomes clear because you want to look at the darker graph and compare it with the corresponding other graphs which are there in the background. And again, because the data that you want to plot on your x-axis or y-axis becomes lesser, it becomes much, much clearer for the person who is reading to be able to identify clearly what is happening to the graph at a 0.1, or etc., etc. So this is what the difference is. This is absolutely black and white, gray, not looking very enchanting when you look at it. But definitely the right one is more meaningful because it is capable of telling you what exactly you want to show your audience. Is that clear? If you have any doubts, please put it. So these are some basic rules that you must follow when you are drawing a graph. In addition to that, I just wanted to mention what are the different types of graphs that we can do and what are the different functions that we plot in a graph, especially when we are working on physics problems. Okay, so the different types of graphs that we do in a classroom are bar plots, linear plots, pie charts, and scatter plots. Okay, when each one of them can be highlighted or can be used, I just want to mention it. So I've shown you over here. The yellow bars over here is a bar graph. You do a bar graph when you want to show what is happening to one with respect to the others. So the comparison becomes easy. Therefore, the bar graphs are plotted one close to the other, and therefore you can highlight what is the differences between them or what are the similarities between them. That is enough. You may also draw a linear plot. A linear plot is you're taking the midpoint of a particular reading and you're again taking a midpoint of another reading and then joining it by a straight line, saying that if there was any gradation from this particular range, I'm not able to show the, from this range to this range, how it has decreased. It has decreased linearly like this. So you can draw a linear plot between this point and this point. Similarly, you can draw a linear plot from this point to this point and so on. That is, you are only going to tell what has happened from here to here. You're not talking about the overall changes of all the graphs. Then you can join them by linear plots. And when do you do a pie chart? Pie chart again can be done when you want to compare one thing with the other. So many things have happened. Something was 40%, something was 30%, something was 13%. You can all draw it as different sectors on a circle. It becomes very clear. Since it is been colored also, you can say that this was much bigger than this was the smallest, and this was bigger than this, and so on. So this sort of comparison is clearly possible with a pie chart. So when you are doing some sort of a comparison, then these graphs are fine. It will be beautiful to draw them because they look colorful and they are very obvious. But many a times we do experiments and we want to show how the variable is changing. But in a classroom, because of paucity of time, we will have to do only a few data points, probably 6 data, 10 data points, and you want to tell the audience that this is what was happening between this value to this value, then you're giving a wider range, then it is necessary that you have to draw them with scatter plots so that there is a gradual change from one point to another. There is some internet connection instability. Can you hear me? Can you hear me?
Yes,
Hello?
ma'am. Yes, ma'am.
Yeah, okay,
Yes,
fine.
ma'am.
So it is best to draw scatter plots and join these dots with a smooth curve, which we generally tell our students to do it in the classroom. I guess you have understood why we ask you to draw a scatter plot. So what are the different types of functions that we will be dealing with in our physics problems? I'm just naming a few of them that we use in our regular course. These functions are linear, quadratic, power functions, polynomial functions, exponential functions, logarithmic functions, sinusoidal functions. These are basically what we deal with in our classroom. And in all these functions, it is written over here, y is equivalent to the function of x. So what is x? X is the argument or the input of the function, and the corresponding function is equivalent to the output y. So this is how a function is expressed. I'll talk about each one of them separately for a few minutes, then we will go ahead. So what is a linear function? All of us know about it. We have done it in our classroom many, many times, but in any case, I would just like to make a mention of it. The linear function is of the type y is equal to mx plus c, where m is the slope of a straight line and c is the y-intercept of the straight line. So what does it tell? Here in this equation, m is the slope, it is a constant, and c is the intercept, which is also a constant. X and y are the variables. Okay. So if you have plotted a function of this type, I've given an example, 2-3 examples over here. This is how the graph will look. For example, suppose your function y was equivalent to x, then it would look like the red line over here. Okay. Now what does it tell? Since y is equivalent to x over here, the slope is equivalent to 1 and there is no intercept. So what does it mean? It means that the intercept on the y-axis over here is equivalent to 0. Y-intercept means at x is equivalent to 0, what is the value of y? So it is showing that since c was equivalent to 0, it should pass through the origin. And in addition to that, since your slope is equivalent to 1, it should be a straight line which makes an angle with the x-axis. This tan of this angle is known as the slope. Okay, the tan of this angle is known as the slope, which since it is equivalent to 1 must be equivalent to 45. So the tan 45 is equivalent to 1, or it is having a slope over here, which is dividing this quadrant into 2 halves, and it is passing through the origin because the c value is equivalent to 0. On the other hand, suppose you had an equation y is equivalent to x minus 3. Then what is the difference between this and this? There is an additional intercept minus 3. So if you look at this blue line and the red line, you realize that both of them had the same slope and therefore they are parallel lines. But since this had an intercept equivalent to minus 3, this point, the blue line, touches the y-axis at x is equivalent to 0 at a value equivalent to minus 3. So if you look at it carefully, this point is at a value equivalent to minus 3 when x is equivalent to 0. That is what the equation is telling us. If on the other hand, you had an equation of this type, y is equivalent to minus 2x plus 3, then what is the difference? Again, all these while these two previous equations had your slope equivalent to plus 1, while in this case, the slope is equivalent to minus 2. And therefore, what is the difference? Look at this. In this case, this angle was acute. In this case, the angle was acute. But over here, angle is always measured from the x-axis in the anticlockwise direction. So if I go like this is an obtuse angle. And therefore, the slope is equivalent to minus 2. If you look at this line, you can see the inclination of this line as compared to the inclination of this line. This was sloping towards the right. This is sloping towards the left. So that is why this slope is equivalent to minus 2. Okay, no minus. And why 2? Whenever we want to find out what is the slope, the best way is to find out the tan of this angle, which is also equivalent to tan of this angle. And hence, it should be equivalent to this distance divided by this. Since the value is equivalent to minus 2, if you look at this carefully, this distance is 2 times this distance. Therefore, the ratio is equivalent to 2. And that is what is represented by the slope of this equation as minus 2. Okay. So by looking at the graph itself, can you find out? I'll talk to you a little later. I'm in a workshop. Okay. Right. If you look at the graphs itself, you can immediately find out what is the slope and what is the intercept, and therefore write the corresponding function because you know the slope m and you know the intercept. Write it in the form y is equivalent to m times x plus c. That will give you the corresponding function that you are looking for from the graph. Okay. So here I'm showing, this was mathematically, I was mentioning what the straight line graph looks like. But in physics, we do have plenty of cases where it is a straight line. For example, I've given a few of them over here. When I'm talking about the force, and I say that the mass of the body is a constant, then force is equivalent to m into a. So as force increases, the acceleration increases. Therefore, if I plot F versus A, I would get a straight line. Similarly, if I'm talking about the energy of a photon, I can say that the energy is directly proportional to the frequency. And therefore, it would give you a straight line if I plot E versus frequency, where H is the constant. Similarly, I've shown a few of them. I don't have to read it. So in each case, it will give rise to a straight line if I'm plotting this versus this versus this, and so on. Okay. I'm showing over here a graph that it is linearly proportional. And in this case, since we are having a equation, V is equivalent to U plus AT, I can say V minus U is directly proportional to T, which is representing a straight line, where A is the acceleration and it is a constant. So all these phenomena would give us a straight line if we plotted Y versus X. Okay. I'm giving another example just to make it clear what exactly I mean by a straight line and how you can calculate slope and intercept, and a little more in detail, purposely because we will be using straight line in most of the cases. Okay. So suppose I have a resistor where I'm changing the temperature. Then the resistance varies with temperature given by this equation. RT is equivalent to R0 1 plus alpha T. If I want to say that as the temperature is increasing or changing, what is happening to the resistance is given by this equation. And if I look at this equation, will I be able to say what should be the slope and intercept? Not really, because there is a bracket and it is not written in the same format as if we were looking at this equation, y is equivalent to mx plus c. But the moment you take out the bracket, you will realize that if you want to find out how the resistance is varying with respect to temperature, and if it is given by this equation, therefore you can immediately say that your alpha R naught must be the slope of that equation line, and R naught will be the corresponding intercept on the y-axis. Does this become clear? Immediately you know that, okay, for this is the straight line equation, then this must be the slope and this must be the intercept. And you can immediately find out if you have plotted R versus T, and if it is a straight line, you can always calculate the slope and the intercept easily, as we mentioned it in the previous case. But please note, in physics, whenever you are finding out anything from a graph or otherwise, it is very, very important for you to write the corresponding units. If your resistance is being measured in ohms and the temperature is being measured in degrees centigrade, then the slope is nothing but the delta y divided by delta x. That is how we are calculating the slope, and therefore the corresponding units must be mentioned. Similarly, when you are finding out the intercept on the y-axis, the corresponding unit on the y-axis should be mentioned for the intercept. So these units are equally important and you should not neglect them. Right. Now, why did we plot a graph? We want to find out the constants of that particular resistor. What are the constants? R naught is the resistance at 0 degrees and alpha is the temperature coefficient. So I want to find out these two values. But looking at the slope and the intercept, can we find out alpha and R naught? If you look at it carefully, you know the answer. Yes, it can be found out. The intercept itself is giving us R naught. Therefore, R naught is known. But I want to find out alpha. The slope gives me R naught alpha. And therefore, if I want to find out the temperature coefficient of resistance, I should find out slope divided by intercept. That will give me the alpha value. And again, the alpha value should be represented with respect to its corresponding units without fail. Okay, but this is not enough. After having found out the value of alpha and R naught, if you are displaying this value in your graph or in your report, you are telling the world that, yes, I have found out the value of alpha and the value of R naught perfectly well, and these are the values. But in experiments, this is not true. You will have some sort of error when you are doing an experiment, and all your values should be having the corresponding uncertainties that are involved in that particular experiment. That is what I want to highlight over here. So I'm showing the graph, how exactly it has to be drawn. Okay, I'm just showing you some values, and from that, the graph tells you what should be the intensity, how it has to be represented. So if you look at it carefully, let us say we took a resistance wire, a copper coil, and put it in an oven, measured the temperature, increase the temperature of the oven, measured the temperature with a digital meter, and found out the corresponding voltage across the resistor and noted down. So at different temperatures, you noted down the corresponding voltage using a multimeter. Let us say the voltage changed from 156 to 232, and therefore you would have used probably a 400 millivolt range to be able to take all the measurements in that particular scale. That's what we have done. Now, this experiment was done at a constant temperature, and obviously all the constant values that you have taken should be mentioned, and therefore you say that when I did this experiment, the current in the circuit was equivalent to 5 milliamperes. Once this is given, and you need to plot the graph and find out the value of R naught and alpha, what do you need to do? Now, since you have used a digital meter, you need to find out what is the least count of that digital thermometer. Suppose I say that, yes, I was using a digital meter which was having a sensitivity of 1 degree centigrade. Then I know immediately, though that the temperature I have measured is equivalent to 30, it must be having an uncertainty at least plus or minus 1, and therefore that has to be represented. So if it is constant for the entire all the values in that column, you don't have to write it for each of these values. Once if you have written it on the heading, it is clear that the uncertainty of 30, 40, 50, 60, etc. was plus minus 1 degree centigrade. So that gives you the uncertainty of the temperature. How do you find out the temperature of the uncertainty of the voltmeter that you have used? Now, all your voltmeters, the voltmeters that you are using or the corresponding multimeters that you are using are supplied with a manual. If you look at the manual, you will realize that the uncertainties are measured for different ranges. If I have used, let us say, 400 millivolt range, then in the manual, I get the data. It says that the uncertainty is 0.5% reading plus 1. So that once I know this, I can easily calculate what is the uncertainty of the voltage. So I write the uncertainty of 156.2, 162.4, etc., calculated using this formula. And then I realize that all of them are changing or having an uncertainty from 1.8 to 2.2, which on an average I can say is equivalent to 2. If I don't want to mention it differently for different readings, I can take an average value because the change is not very far from each other. So I can say that, okay, the voltage was having an uncertainty of 2 millivolt, just to make it a little simple. Okay. So once you know the uncertainties, you need to plot the data. So you have a data 30, 156.2, but 30 was not absolutely 30. It had an uncertainty of plus minus 1. Similarly, the voltage had an uncertainty of plus or minus 2 millivolt. So that has to be represented for each of the points that you are plotting. All of us know how to plot a point. So here, if I have plotted a point on the x-axis, okay, on the x-axis, this uncertainty, this bar over here on the x-axis shows the uncertainty of 1 degree. Similarly, the bar on the y-axis is showing the uncertainty of 2 millivolt along the y-axis. Since the uncertainties were same, all of them are having crosses of different similar dimensions, one along the x-axis and two along the y-axis, to tell us that each of these points had these uncertainties. And then you have to draw a straight line. You know that it is a straight line, and therefore you have to draw a best fit line. Please note it. Now, how do you do the best fit line? Since you have plotted all these points, try to make a line such that all the points that you have plotted lie either on the line or equally distributed on either side of the line, which means to say, suppose I have 10 points over here. Suppose 3 of them are only on this line. Then another 3 of them may be above it and another 3 of them may be below it. If they are equally distributed at almost equal distances, then you have drawn the best fit line. If you are not using an application, then with the help of a scale and by rearranging your point on a scale on the points, you should draw the best fit line. Once the best fit line is drawn, you can easily find out the slope and the intercept. We know about it. Or if you are using an application, you can write the corresponding equation of the best fit line, which will tell you that the equation is of the type y is equivalent to mx plus c. Therefore, the slope is equivalent to this much and the intercept is equivalent to this much. So immediately you know what is the slope and the intercept. I've also highlighted something over here which says that the r squared value of my line that I've drawn is 0.9997. It is a statistical data to tell you that the points that we have plotted is very good to give you a straight line. If you have this r squared value anywhere between 0.96 to 1, then it is a very good line that you have drawn. So that should be an indication to tell that your line is good or bad. Finding out the slope and the intercept, you still do not know what is the uncertainty of the slope and the intercept. But it is necessary for us to tell the world that yes, there is an uncertainty in my slope. There is an uncertainty in the intercept and how much it is. And therefore, the calculated value of alpha should have a corresponding uncertainty and how much that is. So that's what I'm showing over here. Another thing that I have done over here is, if you remember, I was talking about resistance, but I've plotted a graph of V thing and T. I've plotted V over here and T over here. Is that enough? Yes, it is enough. But in this case, we have got over here the slope delta V divided by delta T. Okay, but I want to find out in terms of resistance. Since the current is known, I can find out voltage by current and that will give you the corresponding resistance, which I have shown over here. In this case, the slope was equivalent to 0.6354 and the intercept was equivalent to 137.16. But when I'm writing over here, intercept, I'm writing it as 27.52. Why? Because this value was in volts. So 137 divided by 5 would give you the corresponding resistance in intercept in terms of resistance. And I've written over here, R naught is equivalent to 27.52. I hope it is clear to you. Now I want to find out what is this uncertainty in the slope. So I'm showing you over here. If you know the uncertainties of each of these points, then you can draw another line, probably starting at this point, the maximum uncertainty on the positive side, to the minimum uncertainty over here, that is on the negative side. Draw a straight line. And again, draw another line which starts from this lower point over here and goes up to the higher point. If you look at this dotted line, orange and purple, they are not exactly matching with the solid line that you had drawn first. So what is the difference? All three of them have different slopes and different intercepts. So if we can find out what is the slope of each one of them and also the intercept of each one of them. The intercept of the solid line we have already found out. Slope also we have already found out. Now these two, let us say, has a slope equivalent to m1. This has a slope equivalent to m2. The difference m1 minus m2 divided by 2 will give you the uncertainty of the slope m that you have calculated for the solid line, which will help you to find out what is this value. Similarly, you have an intercept of this orange line as C1, intercept of this blue line as, let us say, C2. Again, C1 minus C2 divided by 2 will give you the corresponding uncertainty in your intercept. And that is what this is the intercept uncertainty. This is the uncertainty of alpha, but the uncertainty of slope is equivalent to m1 minus m2 divided by 2. In this case, we found out alpha from the ratio slope divided by intercept, as I showed you in the previous graph. If you remember, I said alpha is equivalent to slope divided by intercept. And therefore, the slope, the uncertainty in the slope need to be calculated because it would have propagated from the uncertainty of the slope and the intercept, which can be done very easily by taking the quadrature sum. What do you mean by that? Delta slope by slope, the value was alpha was equivalent to slope divided by intercept. Therefore, the uncertainty of alpha, delta alpha by alpha whole squared is equivalent to delta slope by slope whole squared plus delta intercept by intercept whole squared. And hence, delta alpha can be calculated using this formula. I'm not spending much time on this. This last year, we had given a talk on uncertainty of a talk on uncertainty. The link is given over here. Anybody who is interested in knowing how it is, etc., can go through this video and watch out how exactly uncertainty is calculated under different situations. That would be one thing. Nice. Okay. Okay, so here I have just mentioned whatever I told you. Don't have to bother. Okay. So then we were talking about linear equations, how to find out the slope and intercept, and also the corresponding uncertainties. That is very, very important for all our purposes, which we must understand very clearly and use it. In addition to that, all the graphs that we draw in the laboratory are not straight lines. They are of different types. What are the different functions that we encounter in our physics problems? I'm just going through them one by one. I mentioned it previously that there are functions which are quadratic, which means the equation of that quadratic thing would be equivalent to y is equivalent to ax squared plus bx plus c. The c is hidden over here. I'm sorry. This is c over here. So this is the type of equations if you get, then the corresponding graph would be a quadratic graph. How does it look? In this case, your a, b, and c are constants, and of course, y and x are the variables. When you plot a graph y versus x, which is satisfying this equation, you will always get a parabola. That is what is the type of curves that I'm showing over here for a quadratic equation. Let's look at each one of them to understand a little more. If this equation y is equivalent to x squared, okay, shows you a red curve. It is a parabola. Here, your a is positive, and therefore the parabola is facing up. Okay. On the other hand, if I look at this blue curve, this equation is equivalent to y is equivalent to minus 2x squared plus 3. Here, because your a is negative, this curve is facing downwards. So in general, you can say that whenever your a is positive, it will be a parabola facing up. Whenever your a is negative, the parabola will be facing down. That is in terms of a. Now, what does b give us? In this equation, b is equivalent to 0, c is also equivalent to 0. In this equation, your b is equivalent to 0, c is equivalent to plus 3. But in this equation, your b is equivalent to minus 5 and c is equivalent to 3. So let us look at this gray graph first to understand what b is doing, and then we will generalize it. If we look at this gray curve, because a is positive, it is facing up. If you look at this vertex, it has moved from the y-axis by a distance equivalent to 2.5. If you look at this point, you will know that it has shifted from the y-axis by a quantity equivalent to 2.5. And what was your b value? The b value was equivalent to minus 5. You will realize that whatever is your b value, the shift from the y-axis is equivalent to minus b by 2. Because your b over here was equivalent to minus 5, you have a shift over here, which is equivalent to plus 5 by 2, which is equivalent to 2.5. Is it true for all curves? You will realize it. Yes. Here, I'm sorry. Here your b was equivalent to 0, therefore the vertex has not shifted from the y-axis. Here again, the b was equivalent to 0, and therefore the vertex is not shifted. I'm showing it ulta. This is for the red curve, and this is showing from the blue curve. They have not shifted. But in this case, because your b was equivalent to minus 5, it has shifted by a quantity equivalent to 2.5. So by looking at the curve and by looking at the shift, you can have a value of how much the b is for your corresponding function. Again, what does c tell us over here? Let us look at the c value. In this case, c is equivalent to 0. Here c is equivalent to plus 3. Here c is equivalent to plus 3. Your c value is the value of the intercept on the y-axis when x is equivalent to 0. That means when x, if you put x is equivalent to 0 over here, y is equivalent to 3. X is equivalent to 0 over here, y is equivalent to 0. X is equivalent to 0 over here, y is equivalent to 3. So it is giving us the intercept on the y for x is equivalent to 0 is y is equivalent to 0 because your c was equivalent to 0. In this case, sorry, can you hear me? There is some sort of unstable internet. Okay, in this case, because your c is equivalent to 3, the intercept at x is equivalent to 0 is equivalent to 3. Can you see this? It is intercepting at this point, y is equivalent to 3. Similarly, over here, since the intercept over here is equivalent to 3, At x is equivalent to 0, the intercept of the gray axis is also equivalent to 3. It is cutting the y-axis at the point x is equivalent to 3. This is 3. Okay, so this gives us the intercept at x is equivalent to 0 on the y-axis. This gives us the shift in the vertex with respect to the y-axis. The shift is equivalent to this quantity minus of this quantity divided by 2. And the value, positive or negative value of A tells us how the curve is thinking. So by looking at it, immediately you know what is the value, or at least what is the nature of A, B, and C by different. And most of your physical quantities will depend upon the value of A, B, C. So if you can find out the value of A, B, C from your graph, then indirectly you are also finding out what is the what physical quantity that you are looking for from your graphical representation. So that I'm showing you over here in terms of physics where we use these type of functions. In all these cases, when you are putting a freely falling body, if you put a body thing in the vertically upwards, etc., in a in parabolic motion, the equation is of the type S is equivalent to ut plus half at squared. Isn't it a parabolic curve? If I plot S versus t, I will get a parabola. Then looking at the value of this quantity is equivalent to your A, this quantity is equivalent to B, and C is equivalent to 0. By looking at that, you will be able to find out what is your half A, what is your U, etc., etc. So I'm giving a few more examples. All of us, I guess, know what a thermocouple is. If you take two metals and make two junctions, one of them at a higher temperature and the other one is at a lower temperature, if you connect a voltmeter in this circuit, you will realize when this temperature is different from this temperature, the voltmeter will show you some reading, which is known as the thermo EMF. And the thermo EMF is related to the temperature difference by this equation. E is equivalent to AT plus BT squared. Again, if you plot E versus T, E is the thermo EMF and T is the temperature, you would get a parabolic curve. From the parabolic curve, you can find out the constants A and B, which will tell many things about the thermocouple that has been used. Similarly, if you are finding out the variation of resistance with respect to temperature, I'm giving a few examples in physics to give you the relation between why we should talk about a quadratic equation, because many of our processes are quadratic in nature. So if I'm talking about a high temperature difference, how that resistance is changing, then the equation is not just 1 plus alpha t, but it is equivalent to 1 plus alpha t plus beta t squared. And if you plot r versus t, you would get a quadratic function, and etc., etc. You should be able to find out now. The other type of function that we deal with are power functions. Now, what is a power function? If you look at this equation, y is equivalent to ax to the power n is called a power function, where a and n are constants and x and y are variables. So here I've written that a and n are constants. Now, what can be the value of n? N can be a positive integer, it can be a negative integer, it can also be a non-integer. So in different cases, if n is positive, how it behaves. If n is negative, how it behaves, negative integer. If it is a non-integer, how it is behave, or how the graph looks like. So I've plotted them separately to tell you how exactly they would look like and what are the features from the graph you can find out. Now, if you look at this equation, if I say that a is a positive integer, x can have any values starting from plus infinity to minus infinity. That's what I have mentioned over here. That for this equation, I have not mentioned anywhere else, but I'm just showing you the domain is from minus infinity to plus infinity. That means your x values can change from minus infinity to plus infinity. Any value on earth can be the x value. And if your x is positive integer, that means this is positive, then all your curves, look at this, sorry, y is equivalent to x to the power 4, y is equivalent to x to the power 2. In both these cases, your n is positive integer and it is even. Okay, but in this case, y is equivalent to x to the power 1, or y is equivalent to x cube. Here it is positive, but it is odd. So if it is even, the curve is occupying only the first quadrant and the second quadrant. But if it is odd, it is occupying the first quadrant and the third quadrant. So what does it mean? If you look at this curve over here, you immediately know that it has to be an odd function. While if you look at this curve, you know that it has to be an even function. In addition to that, what else do you know? Suppose I put over here x is equivalent to 0. If x is equivalent to 0, 0 to the power anything is equivalent to 0, and therefore y must be equivalent to 0. Therefore, for x is equivalent to 0, all these power functions, for whenever it is positive, will have your y equivalent to 0. If you look at all the curves, they are touching the point x is equivalent to 0, y is equivalent to 0. In addition to that, suppose I put x is equivalent to 1 over here. Then your equation will become y is equivalent to a 1 to the power n. 1 to the power n is equivalent to 1. And you can find out the value of a y is equivalent to a. This is your a value. In all these cases, your a was equivalent to 1. And therefore, all the curves are touching at this point at x is equivalent to 1. Okay, this is true for x is equivalent to minus 1 also. When x is equivalent to minus 1, your y is again equivalent to 1. If it is even, and look at it carefully, you will realize. So here you see that when x is equivalent to 1, this is the value of y, which you can find out and tell that this is the value of a. Similarly, if you are looking at the x is equivalent to minus 1, you can find out what is the value of a. So there are two ways of finding out a from these graphs. Okay, so this is the nature of the curve from which you can find out the value of a and mention whether a is even or odd by looking at the curve itself. What more? We'll see it. If the the exponent n is a negative integer, then what happens? Then the equation will become y is equivalent to a x to the power minus something, which I can write it as y is equivalent to a divided by x to the power the positive number n. So in this case, when x is equivalent to 0, y would become undefined. And therefore, all these functions you will see at x is equivalent to 0, y is equivalent to infinity. They are not touching the point anywhere. They are undefined. So if you're looking at the curve itself, you should be able to tell whether it is a positive integer or a negative integer. Again, when x is equivalent to 1, if you substitute the value, you will find that at x is equivalent to 1, y is equivalent to a over here. If it is negative and even, if x is equivalent to 1, y is equivalent to, x is equivalent to minus 1, y is equivalent to a over here, if it is even and negative. Okay, but if it is odd, then you will have when x is equivalent to minus 1, this is equivalent to minus a. And in all these cases, a is equivalent to 1. Therefore, each time we are seeing that it is equivalent to 1. I hope you have got a gist of it, not spending too much of time, but it is very clear from the graph itself that these are the facts that you can find out from the graph itself. What if the point is a non-integer? Let us say it is a fraction between 0 and 1. And therefore, if you have equations like this, here I am showing x to the power half, x to the power 1/3, x to the power 1/4. All these curves will be facing downwards, concave thing downwards, and it is increasing gradually starting from 0 going up. And you will find that for x is equivalent to 0, y will become equivalent to 0 as previously. And when x is equivalent to 1, y will become equivalent to a, which is shown over here. Therefore, all the curves are touching all of them at this point where a is equivalent to 1. In all these cases, a is equivalent to 1. Okay, so these are the features that you can add. There are similarities between all the three graphs because they are our functions. Okay. Now, one important thing, power function, we generally call these power functions by different name, and you must have heard about it. If it is a function having x is equivalent to x to the power 2, then we call it as a quadratic function. If it is x to the power 3, we call it as a cubic function. If x is equivalent to minus 1, we call it as a hyperbolic function, which we generally use in the laboratory. Just wanted to make it clear. There is a basic difference between power function and exponential function. I will talk about the exponential function a little later, and probably you'll realize the difference. I will show it to you. Okay. Now, these are some physics examples where we use power functions. If you look at all these equations, y is equivalent to half at squared. Your initial velocity is equivalent to 0 for a free fall. Or you are talking about Newton's second law, F is equivalent to ma. Or the volume is equivalent to L cube. All these are having positive integers, t squared, a to the power 1, L cubed, etc. So they are positive exponents, power functions with positive exponents. If you look at these equations, we know about electrostatic force is equivalent to some constant q squared divided by r squared. We know that the gravitational force is equivalent to g m1 m2 divided by r squared. In all these cases, the electric field due to a dipole is equivalent to minus k, some constant, p, the dipole moment, divided by r cube, that is along the bisector. If you're talking about the electric field along the axis of the dipole, then it is equivalent to, again, 2kp divided by r cube. Now, all these equations are similar type. You have r to the power 2, which I write it in the numerator. It is r to the power minus 2. Here also r to the power minus 2, r to the power minus 3. So all these are having negative exponents, but they are power functions. So if you plot over here f versus q, you should get some curve, which we were talking about in the previous slide. And in these cases, time period of a simple pendulum is equivalent to 2 pi root of L by G. So T is L to the power half. In the case of velocity of a sound in air, it is equivalent to P to the power half. In the case of, let us say, Kepler's law, T is equivalent to the semi-major axis to the power of 3 by 2. In all these cases, L to the power half, P to the power half, A to the power 3 by 2 are all power functions with non-integers. So the graph that we were seeing should be the type of graph that we will get if we plot a curve of T versus T, L, or V versus P, etc., etc. Now, this one thing I would like to make it clear before we go ahead. Now, I'm just giving an example over here. Suppose you have a function of this type, minus 7x squared, 5x. If you simplify it, you will realize that it is equivalent to minus 35x cubed. Is it a power function? Since it is x cubed, you tell yes, it is a power function. On the other hand, suppose you have a equation of this type. Your function is equivalent to minus x plus 2 whole squared. If you open this out, you will get an expression minus x squared minus 2x plus 4. Is this a power function? No. If it has terms x squared, in addition to that, some other x values to the power of something else, some constants, etc., then it is a quadratic function, but definitely not a power function. If you had only x squared, it would be a power function. Similarly, in this case, if you have simply x to the power 4, it is a power function. Okay, so I've given an example over here, which has nothing to do with graphs, but awareness. Suppose you have two data points only. Let us say one of your data point was 4 minus 6, another was 9 minus 9. Will you be able to find out the corresponding constants a and n for this power function? That would be my question. It is easy to find out. If you have only 2 points, then also you can find out the values by using these two data points, finding out two simultaneous equations, and hence find out a and n, which is one simple way of calculating what the power function values are, or what are the values of a and n. Okay. Now, what are the other types of functions that we need to talk about? So one of them is also known as a polynomial. The polynomial is of the type, or it is the equation is y is equivalent to some constant x to the power n plus some other constant x to the power n minus 1, etc., etc., where you can have terms x to the power n, x to the power n minus 1, etc., etc., down up to x to the power 1 and x to the power 0. When the term is x to the power 0, this is just a constant, and all other terms are having some powers of x. Then this function is known as a polynomial. But we generally will not deal with such complicated polynomials. Generally, we will deal with x to the power 3 or x to the power 2, etc. So the highest value n gives us the order of the polynomial or the degree of the polynomial. In physics, in lower classes, we will be dealing with probably 2 or 3, not more. So I'm just making you aware of it, because it won't be anything complicated. Now, if you look at this expression, If I put x is equivalent to 0 over here, immediately all these terms will become equivalent to 0. So y will become equivalent to a0. So that is the point that you can determine definitely from your graph. At x is equivalent to 0, this value will give me the value of this constant, which is identifying this particular graph. Similarly, over here, x is equivalent to 0, the red curve will tell me what is the value of your a0. So if you look at this expression, you know that over here it is equivalent to 6, therefore this is equivalent to 6. Here it is equivalent to 0, and therefore here it is equivalent to 0. So by looking at this value, you know this constant is 0. What else do you need to know? You can also find out the nature of the polynomial or the degree of the polynomial. If you look at the curve, this curve has maximas and minimas. If you count the number of maxima and minima over here, you will find that there are 4 of them. This was a 5th order polynomial. And while it has 4 maximas and minimas. So the number of maxima and minima plus 1 is equivalent to the order of the polynomial. If you look at this curve, it is x to the power 4, but it has 3 maximas. So if you are able to plot the entire curves having all the maximas and minimas, then you can also talk about the corresponding order. But generally, with the values that we take in the laboratory, it's not very easy to draw the entire plot for the ranging from some lower values of x to higher values of x. So this may or may not be useful, but definitely polynomials are very, very useful for generating smooth curves in computer graphics. And that is why it is so very important for people who are doing computer languages and graphics will realize that it is a very important function that they need to know. Okay? And the other function that we deal with in our lab is the exponential functions. The nature of the function is y is equivalent to a b to the power x. Please note, in the power function, we had a x to the power something, but here it is a b to the power x. That is the difference between power function and exponential function. This is an exponential function where x is the exponent of that constant b. Here a and b are constants and x and y are variables. What do you mean by this expression? How does it behave? I just want to tell in short. Not able to move it. If you look at this, when b is greater than 1, this constant, if it is greater than 1, then if you look at this number, it will grow. And therefore, it is known as a growth, and it is exponentially growing. When b is equivalent to 1, it is incidental. So there is nothing much that you will learn from it. When b is equivalent to 1, it will just become y is equivalent to a, which is a horizontal straight line, which we think need not bother about it in exponential growth or decay. But when b lies between 0 and 1, if you plot it, you will get a decay. Now, what exactly decay and growth shows? I'm just showing it to you with a particular gene. Okay, I'll show it to you. Can you see it over here? I'll do it once again. You're seeing an you're seeing an apple over here. Okay. Just see as time goes by, what happens to the apple. It is decaying, 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 and it will go on and on and on and on. I don't know how long, for an infinitely long time, till it decays completely to nothing. And therefore, this is what is known as an exponential decay. I'll show you a growth also, just a few minutes. Right. Let me talk about the graphs first, and then we will go to growth. This is irritating. Okay. Right. So if you look at this, the equations are y is equivalent to 4 to the power x, e to the power x, 2 to the power x. In all these cases, b is greater than 1. And therefore, it is representing a growth. It is as x increases, it gradually grows and it is concave upwards. This is an exponentially growing curve. Exponentially growing curve. But on the other hand, if your b is between 0 and 1, half and 1/4 and all that, then the curve is like this. It gradually decays as x keeps on increasing and becomes extremely small when x is very, very large. So this is a decay curve. It is an exponentially decaying curve. Where do we see this decay thing, growth and curve? Okay, Suppose you are talking about sunlight reaching the depth of the ocean. I've written that over here. Then what do you think will happen to the intensity of light? It will gradually keep on decreasing and it will become lesser and lesser and lesser. That is a case where it is exponentially decaying. On the other hand, suppose you keep some money in the bank and you are getting interest. That interest is getting added to your principal. Then as time progresses, your money will keep on increasing, which is an exponential growth. So that is how we require these, because in many of our physics problems, we have exponential growth and decay that we are dealing with. We need to know about it. Okay. Another thing that we require is logarithmic functions. I think I should not have this somewhere. Logarithmic function, so which is of the function y is equal to a cos x plus b. If you plot this curve, this is how it looks. Gradually, it will be increasing, but the increase is not as much as when x is increasing to a large amount. The increase in y is gradual, and it is bending down like this towards the x-axis. Over here, the peculiarity is when x is greater than 1, then it will be increasing. Y will become positive. When x is lesser than 1, then it will become negative. So you have a curve over here, which is going down to negative values for small values of x, and it is positive values when x is large. The change of y is smaller as compared to the value change in x. That is what is meant by saying that it is a logarithmic function. Okay. And what else you can find out? I think I will not spend much time over here. Okay. And the last type of functions that we deal with in our laboratory are sinusoidal functions. Where do we see them? If you look at a pebble thrown into a water, you will get a wave. If you talk about electric current, voltages, etc., they are all waves. So all of them are examples of sinusoidal functions. Sinusoidal functions are of the type y is equal to a sine bx plus c, where a, b, and c are constants. It could be sine or cosine. A gives the amplitude of the corresponding wave. It is giving rise to a wave equation. B gives you the angular velocity, and C gives you the corresponding phase of that particular wave. So if you look at these graphs, you will realize what it means. Let us say the red graph is representing sine x. That means your A over here is equal to 1, and your B over here is also equal to 1. The red curve is over here. It gives us the angular velocity, or it just, let us say it is having one wavelength. Okay. And the amplitude of this is equal to 1. Therefore, this value, the maximum value of the amplitude of the wave is equal to 1. If you look at the blue curve, y is equal to 2 sine 3x. 2 is the amplitude. Therefore, the wave is having a greater amplitude over here. Maximum value being equal to 2. And it has 3 over here for B, which tells us that this wave, one wave, another wavelength, 3 of the wavelength are there in the previous value, which was expanding from here to here. We have 3 such waves over here. That is the number 3 that is shown over here. Okay. In the third type of equation, y is equal to sine x minus 1 by 5, 7. Here your B is equal to 1, A is equal to 1, and C is equal to minus 1.57. So look at the difference over here. Amplitude is equal to 1. The maximum value of the wave is equal to 1. B is equal to 1. If you look at this, the entire space from here to here, there is just one wavelength from here to here. It is one wavelength. That is what is represented by this 1 over here. It has a value C, which is equal to minus 1.57. If you look at this curve, this is the shift of this green curve with respect to this. It has shifted by a quantity equivalent to 1.57, the positive x direction, when the C value is equivalent to minus 1.57. That is what this C represents, or the corresponding phase of the wave with respect to this position. That is what the wave equation is representing. So by looking at the curve, should you be able to find out the amplitude? Definitely, yes. You look at this value, you know what is the amplitude. You look at the wave, how many waves are there in particular range, which is equivalent to, let us say, equivalent to 2 pi. This is equivalent to 2 pi, 0 to 2 pi. If it is 1, then your b will be equivalent to 1. If it is 7, then the b is equivalent to 7, etc., etc. And if you look at the position with respect to your 0, what is the position, then you will know what is the corresponding phase. Position means the phase, and you can find out the phase in terms of time or the wavelength. I think need not spend much time over here. So that is how you can calculate or find out the corresponding constants of your phenomena that you are dealing with. Another important thing I want to tell before we go ahead, sometimes it is necessary for us to draw curves and in logarithmic scales. Why do we do it and when do we do it? I'm just giving an example. Suppose you have done an experiment with a high pass filter. High pass filter is a device which, if you give all frequencies, it will only allow certain high frequencies to pass through, rest of them will not be allowed. So obviously there is a cutoff frequency above which the frequencies are allowed, below which the frequencies are not allowed. So if you are studying a high pass filter, you would rather like to find out what is this cutoff frequency above which the frequencies are allowed. So if you do an experiment for different frequencies and find out what is the output in this high pass filter, and hence calculate the amplification factor, which is equivalent to the output voltage with respect to the input voltage, which is mentioned over here, you will find that you will have to take a large number of frequencies to be able to plot a good graph. So here the frequencies have changed from 20 hertz to 6000 hertz, and the corresponding amplification factors are found out. If I say that from this data, I want to find out the cutoff frequency by plotting f versus the amplification factor, I will get a curve like this. It tells us that these values for small frequencies were all very close to each other, and for higher frequencies, they became maximum, and that means all of them are having the same amplification factor of 1. If I have to find out what is the corresponding cutoff, I should say I should know the maximum value. 1 by root 2 of the maximum value, the corresponding frequency is known as the cutoff frequency. So I have to find out what is 1 by, at 1 by root 2, what is the frequency? If you look at 1 by root 2, the number is something 707. At this value, what is the frequency? Since all the frequencies are very close, the error by finding out the frequency would be huge. Therefore, it is not a good way of finding out the cutoff frequency from this graph, because all these frequencies are very, very close to each other. On the other hand, suppose you plotted all the frequencies in the log graph. That's what we've done over here. Instead of plotting t versus f, if you plot t versus log of f, then the graph would get expanded. All your lower frequency curves are over here. The amplification factors are small, but they are all separate like this. And then you find out the higher frequency curve, which we saw is the nature of the log. And over here, if I have to find out the cutoff frequency, I can find out easily what is the cutoff frequency. Then you can say we are finding out log of f. Yes, we can find out log of f and hence find out the value of f from the antilog. That will give you the cutoff frequency. So in certain cases, you will realize that it is necessary for us to draw one of the values or maybe both the values in log graph to maximize the expanse so that it is easy for you to calculate. Just showing this because we use this in a number of cases. Okay. But the most important thing, we saw that all these functions, there are some critical factors from which we can find out the constants, but not very accurately. So what do we need to do in order to get these constants? It is very important for us to linearize the curve. We realize that in a straight line curve, it is very easy for us to find out the slope and the intercept, and therefore it would be ideal if we could convert all of these functions into a straight line curve. So the process of converting into a straight line curve is known as the linearization. And how do we do it? Well, I'm talking about a straight line curve. We've seen how easy it is to find out intercept and slope. So I'm not spending much time. In addition to that, what else can we find out? That I wanted to highlight over here. So in this case, suppose you had all these values of f, m and l, you will get a straight line and hence find out the slope and the intercept from the graph very easily. In addition to that, what you can find out? We said that my data was such that at 2 grams, I found out the extension of the spring. 4 grams, I found out the extension of the spring. This is for a spring data. I don't have any data for 3 grams. Can I find it out? It can be done. If it is a straight line curve, then you can easily find out, because it is linear, at 3 grams, what is the corresponding extension can be found out. And therefore, this is known as interpolation. So from the curve itself, you can find out for any intermediate value from the graph. Again, since it is a straight line curve, you can extrapolate. You can continue making this line straight and expand it. Suppose you want to find out what happens at 12 grams. What would be the extension? If you had this straight line expanded, you can also find out what would have happened or what would be the extension when the load was equivalent to 12 grams easily from this. So for a straight line graph is very beneficial for us because many things can be determined from the straight line very easily. And therefore, it is important to convert most of these functions into a straight line graph. So I'm not spending much time over here. Okay. Now, how do we how do we convert a power function into a straight line graph? I've shown over here. I'm sorry, it is not visible. I don't know how to move it. Okay, I hope you can see it. F is equivalent to A R to the power n. I have a function force which is proportional to some constant A R to the power n. I am not knowing what is the value of A or what is the value of n. If I plot a graph of F versus R, I had shown you before, I would get a curve like this. When I look at the curve, immediately I know that my n must be negative because it is going up, 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 up for small values of R. So it must be negative, but nothing more about it. Why nothing more? We saw that at R equivalent to 0 and R equivalent to 1, we could find out something. But my data points are all starting from 15 to 45. I don't have R is equivalent to 1 or R is equivalent to 0. And those values are very difficult to take in the laboratory. You will realize it when you actually do it. So since we don't have these data points, we really cannot find out much about this graph, the value of A or the value of N, etc. Excepting that you can make us guess saying that N is equivalent to minus value. Okay. But instead, if you could draw a straight line from that, then it would be meaningful. Now, how do you draw a straight line? If you take a log of this entire function, log of F is equivalent to log of A R to the power N. You can write it as log of F is equivalent to log of A plus B times log of R. I'm sorry, you're not able to see it properly, but this expression is ln F, natural log of F is equivalent to natural log of A plus B times natural log of R. Just find out the natural log of this entire function. This is what you will get. Now, instead of plotting F versus R, suppose you now plot log of F versus log of R, then it would become a straight line. It will become y is equivalent to mx plus c, where your m is equivalent to b, c is equivalent to log of a, and y is equivalent to log of m, and x is equivalent to log of r. That is what is plotted over here. I'm plotting log of f versus log of r. I will get a straight line and not a curve like this. Once I get a straight line, finding out the slope and the intercept is not difficult. So if I can find out the slope, I know what is the value of B. If I know what is the intercept, I know what is the value of it. Therefore, both A and B can be calculated from the straight line graph, which will give me my important data that I'm looking for in my corresponding experiment that I have done. That is why it is important for me to draw a straight line graph. So I'm showing you the values over here. If you get a straight line, the corresponding equation will be like this. The slope is equivalent to close to -2. Therefore, we know that R was to the power of -2, which I said was negative. So it is over here. And the intercept is equivalent to 9.7. So the corresponding intercept ln log of A, ln of A was equivalent to 9.7. Therefore, A would be equivalent to e to the power 9.7. So I know the value of A. I also know what is the value of B. Therefore, everything that I wanted to know for this particular phenomena is known. Okay. Suppose you have exponential curve. It's very sad. I don't know how to move this black bars over here. I'm just reading out the equation for you. Suppose you had a radioactive phenomena where n is equivalent to n0 e to the power minus lambda t. If you plot n and t, you will get this curve, this orange dotted curve that I've drawn would be like this. Again, over here, you have some value of 0. You know the value of 1. So you know that, yes, n is a very large number. At n is equivalent to 1, you could find out what is this value and tell that, okay, n0 is equivalent to some number between 400 and 450, maybe 425 or so. So that is all that you know. What else do you know? You really cannot find out the value of lambda from this curve, since it is not a straight line curve. So it is necessary for us to draw a straight line curve. Suppose you have an equation of this type, exponential curve. You can again take the log of this equation. If you take the log of this equation, you will get, I'm taking natural log. So natural log of n is equivalent to natural log of n0. Natural log of e to the power minus lambda t is simply minus lambda t. And therefore, if you plot natural log of n with respect to t, or probably natural log of n by n naught with respect to t, you will get a straight line. So if you plot this now, you will get a straight line. Once you get a straight line, again, finding out the slope and the intercept is very easy. So by looking at the slope, you know what is the value of lambda, and that is a clear indication of what the process was and gives you the idea what this constant lambda is equivalent to. So here you are plotting a graph of log and a linear curve. This is log n, while this is just a linear t curve. While in the previous case, it was log of f versus log of r. That is the difference. But you can do it by taking the log of the entire equation and plot the corresponding factors on the y and x axis to get a straight line. And from the straight line, you can calculate or determine what are the important data that you are looking for. Okay. I'm just showing you over here what exactly an exponential growth is. We have all seen, if you sow a seed and then allow it to grow, initially the plant grows very fast, and gradually as time passes by, there is a stagnancy in its growth. So all such growths are known as exponential growth. I just wanted to show you what exactly growth is. Now, if you have to linearize an equation of this type, y is equivalent to a e to the power bx. I've already told, take the log of this entire equation. So here I've shown y is equivalent to a e to the power bx. The corresponding log values can be either natural or log to the power base 10, whichever is convenient. And both of them will give you a straight line. So you get log of y is equivalent to log of a plus b times x. If you plot this versus x, you would get a straight line where b would be the slope and log of a would give you the intercept, which I showed you in the previous case. This is how I'm generally saying that if it is an exponential function, this is what you need to do. If it is a polynomial function, again, I told you we will not deal with such complicated functions. I'm just giving a simple example. If you have an equation, let us say y is equivalent to v naught t minus half gt squared. Then if you plot y versus t, you would get a parabola. But if you want to linearize this curve, how can you do? Y, over here you have a t, here you have a t squared. You should write it in the form y is equivalent to mx plus c. One way would be, you can divide y, this whole equation, by t. If you do that, you will get y by t is equivalent to v naught minus half gt. Okay, now look at this equation. If you plot y by t on the y-axis and corresponding t on the x-axis, will it not be a y is equivalent to mx plus c form? If so, it will be a straight line. From that, you can find out the slope and the intercept and conclude. Okay, so this is some simple example I'm giving you. There are much more complicated equations. If you have understood this, then you should be able to understand how exactly you can linearize your curve by looking at the corresponding relation or the equation. So that is the end of this. I thought I will try to complete it as quickly as I can. So I think I have done whatever I wanted to do. You can start asking questions. If you don't want to see the PPT anymore, I will switch off and go back to the general mode where I can see you. Is it okay?
Yes, ma'am.
Yeah. Right. Now I can see the chat box and find out what exactly they are looking for. While I'm really sorry for that, though I don't like doing it, but I'm compelled to do it because I'm not able to interact with you. I'm really sorry. Are there any questions? Can I go through that? Can you please explain seismic color map? Okay, seismic color map, I showed you that though you are making it very colorful, what you are looking for is the intensity of the maximas and minimas, which is not very clear. So if you are looking at the intensities, the intensity should be represented clearly. And therefore, you have to choose a color. If at all you want to do it a color map, you have to choose a color, so the color map, so that it is clearly visualized. Okay, that's what I meant by saying that instead of seismic color, you can choose another. I showed you another graph. Okay. Ma'am, I didn't understand this topic. Can you explain it briefly again? Are you talking about the color map? And Arnav Garg? Arnav Garg? I'm not sure whether he is there. In any case, what exactly you want me to explain? Please highlight, I will tell. Ma'am, I didn't understand this topic. Can you explain it briefly again? Ma'am, I have doubts. Okay, you please pinpoint what is your doubt. We will try to clarify it. Okay, Arnav Garg. Arpita. Okay. Is Arnav Garg is there? Okay. Ma'am, please explain scatter plot again. Okay. Now all, shall I go back to the thing? I'll just show you. Please look at this. You're talking about a scatter plot. These are the corresponding data that we have got in a particular experiment. So I'm plotting now 179, 266, 3, I'm sorry. I've plotted actually 1, 421, 2, 355 in this orange curve. And I've plotted 179 in the blue curve. Now let's look at the orange curve. So the first point is at 1, it was 421. At 2, it was 355. What happened to, if I had taken a value in between 1 and 2, what would be the corresponding value of n? I do not know. But I only know that it would be smoothly changing. It won't be an abrupt jump. That means it won't be from 421, abruptly it is jumping to 355, again it is jumping. Therefore, I'm joining it by a smooth curve. That is what is known as a scatter plot. I'm first pinpointing what are the data points and then joining the curve smoothly so that it shows me the corresponding trend in that particular event. So in this case, it is gradually decreasing. It is an exponential decay. It's not, it should not be joining this point and this point by a straight line, this point and this point by a straight line. Then it says it is not gradually decreasing, but it is going linearly from one point to another. Again, the slope is changing. It is going from one point to another with a different slope. Between this point and this point, it will be a different slope, which is not true. And therefore, you are joining with a smooth curve. This is known as a scatter plot. Is that clear? I think it was, yeah, no, this was Rashmita Jena. Rashmita Jena, are you here? I'm not getting any reply. Anyway.
Yes, ma'am.
Yeah, did
Thank
you
you,
understand?
ma'am.
You understood
Yes.
what is a scatter plot?
Yes, ma'am.
Okay, now do you understand why you should draw it as a smooth curve?
Yes, sir.
Okay. Then Arnav Gar, can you explain this again? Yes, please explain this again. But what he is referring to, I'm not very clear. Arnav, please answer once again, question again. Anita Yadav, really interactive session. I am a big fan of your knowledge, ma'am. Are bapre. This is, I don't know whether, anyway, thank you very much. Arham, good evening, ma'am. Could you please recommend some of the graph creating software? Excel is the simplest, easiest, and cheapest. You can use other things also if you have the facility, but it will have to be a paid version, while Excel is a free version, which you have it in your Microsoft thing, Word. software, and therefore you can use Excel. Okay. Ma'am, can you share the link for the PPT? Link for the PPT, I think I will share it in Sopan Ashram. You can have a look at it. Okay. I'll share it with the with Mr. Bimalji. You can have a look at the Sopan Ashram. When the graph is touching infinity, how can we make it linear? Okay. How can you make it linear? Very good question. If you take a curve, f is equivalent to r to the power minus 2, etc. Over here, you have an point where x is equivalent to 0, y is equivalent to infinity. But when you draw a linear curve, you will get a straight line, which will have a y-intercept as well as a slope. Therefore, you can have a point where I showed you with a linear curve for f is equivalent to r to the power minus 2, how it was a linear curve and it has an intercept. So that is how you can do it when you take a log of that value. Okay, right. Rashmita Jena. Sham, did you follow? Sham, when the graph is touching infinity, how can we make it linear? You saw how it can be made linear by taking the log. What is log of infinity? Can you find out? You should be able to answer now. Okay. Darshan Saravanam. Ma'am, can you recommend any open source Python libraries for data plotting? I think there are many. Matplotlib is a open source Python library where you can use data plot. You can use it for data plotting. If you've used it, then it is possible. Even otherwise, you can just go to Python open source libraries and check out. You will be able to find out. Sham Darshan, please try and tell me whether you have got it or not. Any attendance certificate will be issued. Please contact Mr. Vimalji to be able to tell whether certificates will be issued or not. Mr. Bhaskar Vaishnav has already answered to this question. Matplotlib will give you data plotting facilities. Please use it. Thank you. Is there anything else that you would like to think? I think that many questions are there, which I guess I have answered. But still, if you have any other doubts,
Can you explain?
You can send an email to me.
Can you explain a bit about error? How we deal with error?
Sir, please tell me again.
Ma'am, can you explain a bit about error? How we deal with error?
Yeah, it's a lecture by itself. It will take you 2 hours to go through the entire thing. So I would suggest, yeah, please go to the website. There is a video uploaded. Please go through it. If you still have any doubts, you can send me an email. I will answer them. Talking about errors, computer thing will take you another 2 hours. Okay, but go through that video. Spend some time, go through the video, and I'm sure you will understand. In case you still have any difficulty, please get back. I will try to solve it. Okay, my boy?
Okay, ma'am. Thank you.
So somebody is suggesting GeoGebra will also help in plotting. Yes, you can plot with the GeoGebra also. Sham is still insisting, if both are infinity, how do you get a straight line? I think if you take log of that value, you will realize. Okay. Sham, you will plot a graph of the data that is given with of f and r to the power minus 2. Plot a log graph, and you will realize how it has how the point for infinity is also represented on your curve. For r is equivalent to 0, you will get a point on your log graph, and that is the corresponding point you are looking for. Okay. Okay, so thank you very much for your attention. I'm really very sorry for talking to you all for so long without realizing or understanding your requirements or looking at your faces, finding out whether you've understood or not. but I'm very sorry for that. Hope sometimes we will be able to interact one-to-one.
Thank you, ma'am. Do we have any other question? Okay. As we draw this incredible session to a close, I want to extend my heartfelt gratitude to each of you for joining us today. And it has been an honor to have you all participate in this NAEST 2024 webinar, organized by National Anveshika Network of India, NAMI, an esteemed initiative of Indian Association of Physics Teachers, IAPT, and Shiksha Sopan. Today's journey through a fascinating world of know-how of graphs has been truly enlightening. I would like to express my sincere gratitude to Ms. Sarmistha Sahu, ma'am, for her time and for sharing her profound knowledge with us. Her dedication to making physics accessible and engaging is truly commendable and continues to inspire countless students and educators. I also want to acknowledge the efforts of the organizing team at NANI, IAPT, and Shiksha Sopan for putting together this successful event. Your hard work behind the scenes has made this enriching experience possible. Before we conclude, I want to share an exceptional opportunity that awaits you, the National Anveshika Experimental Skill Test, NAEST 2024. Today is the last day to register yourself. This prestigious platform is designed for students from grades 9 to 12, along with bachelor's and master's program in pure science, to showcase their exceptional knowledge and skills in physics. We strongly encourage you to register for NAEST 2024. This program promises to be a rewarding learning experience and a chance to distinguish yourself from your peers. Your active participation and insightful questions today have enriched our discussion, making it a collaborative and interactive experience. I encourage all of you to take the insights gained today and explore further. Let this session be stepping stone to deeper inquiry of learning. Thank you once again for being the part of this webinar. Let's continue to celebrate and explore the wonders of science and education together. See you next year at NAEST 2025. Embarrassing New Year's, new approaches, new endeavors. Have a great evening and best wishes for you for your future endeavors. Thank you. Thank you very much.
I think a big thank you to all of you. Let me put my email ID in the chat box for anybody to interact. If at all, you can send messages by email. Shall I? This is, how do I do it?